What if your resistors are not just in series or parallel? What if your circuit's got multiple loops, it's got branching parts, and it has multiple batteries? This is Kirchhoff's rules, and they let you solve anything. So the big picture idea is that Kirchhoff's rules lets us handle circuits that you can't simplify with normal series parallel tricks. There are two rules, and they're based on conservation laws. Rule 1 is Kirchhoff's junction rule, or charge conservation. At any junction, and we'll look at examples for both of these rules, at any junction, the total current in equals the total current out. This is literally what flows in must flow out, like cars going through a roundabout. Use this to write equations at any point where the wires split or combine. How about the second rule? Rule 2 is Kirchhoff's loop rule, and it's energy conservation. The sum of all potential changes around a closed loop is 0. So all changes in potential added up is a net 0. This means as a charge goes around a loop and returns to where it started, every climb in potential, which is a battery, is always cancelled by a resistor, a fall. Here's an analogy for your intuition. When a roller coaster makes a full loop, it ends at the same height it started, even if it goes up, down, and spins. That's the loop rule. The battery lifts the charge up by a value of 12 volts, and then the resistors drop it by negative 12 volts, then everything balances. It's conserved. So before we solve some problems, here's a little framework that I'll go through. 1. Label all currents and be consistent. 2. Pick your junctions. This is where you would apply the junction rule, and you'll see what this looks like. 3. Pick your loops. This is where you'll apply the loop rule. 4. If needed, use Ohm's law, which is V equals IR. Every single formula we'll use and the two rules are on the free cheat sheet in the description. 5. Solve your systems of equations. So I'll put this up in the corner while we solve problems. You can refer to it. I've drawn out a diagram here and we're going to solve some values for it. First, let's label all the currents. Since currents that are positive travel away from positive battery terminals, and positive battery terminals are the longer sides, then we can have one current coming around like this, traveling this loop path. And if it comes through here and loops like that, we have a second one that we can say is looping clockwise around the top loop. Just call this I1 and I2. Really, it's arbitrary. We actually don't know whether or not I1 is actually going clockwise, but it's not a big deal because if it happens to be going in the opposite direction, then I1 is just going to have a negative sign in our final calculation. Now, final current is after they merge into this path, go through here as I3. So direction is arbitrary. If the current comes out negative, it's just flowing the other way. But see, we know everything. We've been given all the resistances, all the voltages. The unknowns are the currents, and Kirchhoff's rules help us solve for the currents. So our unknowns are I, 1, 2, and 3. Let's start with the junction rule. The junction rule says that all current in equals all current out. And we have 3 unknowns. I1, I2, I3, so we need 3 equations. We're going to have 1 junction equation and 2 loop rule equations. The junction rule, if we start from point A, is this. So at point A, I3 enters, and then I1 and I2 leave. So that means whatever's entering equals whatever's exiting, I1 and I2. This is our junction rule equation. Let's set this equation to the side. Now time for the loop rule. What was the loop rule? Kirchhoff's loop rule says that all changes in potential will add up to a net 0. So it'll be the same as when you started. Changes in potential happen from resistance or when you gain voltage. So let's start with the first loop. First loop is the upper loop, which is following this path. It's the current I1's loop. Goes from A to H to D to C to BA. So A, H, D, C, BA. We start and end at point A. And let's walk the path. So from A to H, we encounter this resistor. That would be negative 60 times I1. That's the first change in potential. If you're wondering why we write the resistance and the current, it's because Ohm's law tells us that the voltage is equal to resistance times current. So that's what we write. From H to D, nothing happens. And then here we have a battery. So since it's a negative to a positive terminal, we gain 50 voltage. And then we bump into this internal resistance. But here's the thing, this path is I3's path. So now we write 1.5 I3 instead of I1. Up here at the 60 resistor, finally before hitting A again, we lose another 40 to the resistor. And this is our first loop equation. It's equal to 0, according to the loop rule. How about the second path? Second loop will take the outer loop A, H, D, E, F, G, A. So this. We could have also chosen the lower loop A, B, C, D, E, F, G, A, but to solve this one, I'll be doing this outer loop. Let's walk through it. Again, we start at point A, and then on our way to point H, we bump into this, -60. Next, from H to D, nothing happens. And then here's where something interesting happens. From D to E, this portion of the track, the assumed direction of the current, if you took a positive test charge and placed it here, it would start to travel this way against the current, or at least what we assume is the direction of the current, which means, and since this is I2's portion, here would be a positive gain, plus 25 I2. If this is a little bit confusing to you, don't worry, because the more you practice this kind of stuff, the more it makes sense. Similarly, from E to F, this internal resistance is also positive. From F to G, we're going through a battery. But the thing is, we lose voltage because we're going from a positive terminal, the long line, to the short line, or the negative terminal. When you're going from negative to positive, you gain the voltage, but the other way around, you lose it. So negative 90. And then we return back to A, our starting point. So here's our new equation, equals 0. Our main work here is done. We've found the 3 equations to represent the 3 unknowns. And that's the hard part. The rest is just algebra and rearranging. So if your math skills are strong, this is easy. Let's start with cleaning up our equations. Let's label them. So this is equation 1, equation 2, and equation 3. That's the order we found them in. We can rewrite this and clean it up a little bit. So I'll quickly do that. I just compacted it a little bit more for readability. And now we're ready to solve. So if we look at equation 3 here, we can rearrange for I2 with our excellent math skills. I2 equals 90 plus 60 I1 divided by 26.5. Or in a more simplified form, 3.4 plus 2.3 I1. This is our equation that's isolated I2. From equation 2, we can isolate I3. So let's make some space. Isolating I3 in this equation is simple. You get I3 equals 50 minus 60I over 41.5. And this gives us 1.2 minus 1.4 I1. So we have some useful equations here. We have an equation for I2, equation for I3, and from the junction rule, we can make ourselves an equation for I1. If you go ahead and substitute in these terms, then you get this. I1 equals I3, which is 1.2 minus 1.4 I1, minus I2, which is 3.4 plus 2.3 I1. So we just substituted in our values here into our junction equation. And the only variable in this equation is I1. So you can easily go ahead, solve for I1 as negative 0.465 amps of current. What's interesting about this is it's negative, so it doesn't flow this way. Our assumed direction was clockwise. Turns out it's opposite. And then guess what? We can substitute this value into here for I1, and then solve individually for I3 and I2, which are 1.878 amps and 2.343 amps respectively. There we go, we just solved it. If the algebra got you a little lost, don't worry, it's what a lot of people are held back by. But if you improve it, physics is easy. So to sum it up, big picture idea for Kirchhoff's rules is if you can't use series and parallel tricks because your circuit's too messy, then you label all the currents, you pick junctions and identify loops to craft equations for all of your unknown currents, and then use algebra, finish it off. Here's a final note to wrap everything up. If you have 2 end-to-end batteries, what happens? Do their voltages combine? Yes. So if you have 2 batteries like this in series, and let's say they're both 1.5 voltage, then your net voltage is 3. However, if they are opposing each other, so I'll draw that really quickly. Say it's like one battery there, and then the other battery is here, but it's flipped. Then what happens? Let's say this one's 20 volts and this one's 12 volts. Your net voltage is 20 minus 12, which is 8. Why? Because they're now opposing each other. So you subtract. It's like 2 people pushing in the opposite directions. And that's all for Kirchhoff's rules.